I go to the main window in ADS and I open a project which is designed for manufacturing project, DFM project, and notice in this folder E, it's DOE on elements. I choose some elements, 5 variables in my amplifier, 5 different variables, and I want to run an experiment. So the number of experiments that ADS will run for me is 2 to the 5th, okay, which is 32 different experiments to cover all the full factorial variables changes that I talked about in my introduction. So let's go to this design. When I open this 5 variable design, here it is. And again, it is, I don't know if you've seen this before in other talks or not, but this is the input matching network that has a capacitor and a resistor. Here's a resistor, capacitor at the input. And there is a middle stage that has the FET, and at the output there is a resistor R1, and there is a capacitor C1 at the output matching network here. And this is the matching network. This is the bias line and the bypass capacitor. So I'm running a design of experiment, and you just choose the DOE controller and you bring it into the schematic page right here. And this is the DOE goals, because we have 3 specifications. We have gain specification, we have noise figure specification, and we have S22, output return loss specification. So you drag 3 of those DOE goals in here. Okay, so now if I zoom, you will see the DOE controller. I chose the full factorial, because once I click on this, there is different DOE experiments you can choose. The 2KMP is the full factorial method that I explained to you. Notice the goals here, noise figure. My maximum noise figure is 1.85. That's the spec. Minimum gain, this is the gain. Minimum gain is 11 dB, and maximum return loss is -15. So I want -15 or lower for my return loss. So these are the spec lines. I put them in the goals here. Okay, so here is my variable, the ones I chose. Notice here in this variable block I have input matching network C1, capacitor C1. The nominal value is 0.9 picofarad, and I have a DOE plus or minus 5%. This one is input matching network R1, resistor R1 is 8 ohms, and I have a DOE plus or minus 5%. Same thing with the output matching network C1, 0.26 plus or minus 5%, and this output matching network R1, which is next to the FET, is plus or minus 5%. Now these are 4 variables. My 5th variable is the width of the lines. I can choose different width as each one, the 10 micron, the 15 micron, the 20 micron, the 25, 30 micron. I can choose them as separate variables, and I can run many more experiments. But I decided in this experiment to put all the width of the line in the design as one. They move up and down together. So what I did is I multiply each of the 10 micron, 15 micron, 20 micron, 25, and 30 micron by a factor 1 plus x. And notice here x varies in the DOE, minus 0.05 to plus 0.05. So this way, this variable controls all the width of the line together, plus or minus 0.05 for this equation. So I have 5 variables now, and all I have to do, I have the setup here, all I have to do is just simulate. And notice when the simulation runs, it produces 32 experiments. Okay, so you can see here it's done, but you can see we have like 32 experiments that were created, and all the calculations were done. Okay, so let me close this and open the the window that gave me the results. This is the results for my DOE experiments. And you remember in my tutorial introduction, I had shown you that this is the Pareto chart. So this is what it's telling me here for the gain spec. It says here, the y-axis, gain spec. The output matching network resistor R1 is contributing 93% of the gain variation. Watch out. By doing this experiment now, and sometimes I have a huge design that has hundreds and thousands of components. By doing this, automatically it's telling me that the resistor R1 is a problem. The next one is the width of the lines. The width of the lines, the gain is sensitive to the width of the lines, but it's only like 5%. Now that I told you that 92% of the gain variation is due to the resistor, this 92% sounds very large for you, but how much is it in dB? Then I go to the effect plots. If you remember, I told you about that main effect plots. R1 here is contributing about 0.3 dB of gain variation. So if my gain of the amplifier is 11 dB, my gain variation, it's going to go from like maybe 10.8 to 11.1 or 10.9 to 11.2. There is a 0.3 spread variation due to the resistor R1. Let me now go to the next spec. We have the noise figure here, and notice in the noise figure now, R1 is contributing about 51% of the noise figure variation, and the width of the lines is are contributing the change, especially in the input matching network for noise figure, but it is contributing about 48% of the noise figure variation. So those are the two dominant effects. We have the R1, the resistor R1, and the width of the lines, especially at the input matching network, is causing some changes in the noise figure. But again, let me ask you, how much variation is that? How many dBs? So we go to the effect plots, and we look at the noise figure variation here due to the width of the lines, and we notice we get 0.015 dB variation in the noise figure. Not too much. So don't be misled by the Pareto chart. The Pareto chart show you big numbers here, but you really have to know how much variation is that. It could be really minimum variation. Now if we look at the S22, notice the output matching network capacitor C1 is causing about 55% of the variation in S22. And notice the width of the line again is causing about 32% of the variation. And we have some interactions now between elements. Notice about 6% of the variation in S22 is caused by interactions between the width of the line and the resistor R1. There is some interaction between that resistor R1 and the width of the lines. Okay, so we look at now the main effects plot, and we notice that the width of the line, E, is causing about 3 dB, the red line, about 3 dB variation in S22. But let me show you something about this interaction. It's important to explain to you how to use this interaction between C and E. Again, C is the output matching network resistor R1, and E is the width of the line. Let's see how we can fix that. Notice the way it is plotted here. The x-axis represents the resistor, which is C. You remember the C is for the output matching network resistor R1. And this is the -1 all the way to +1 change. And this here is the interaction plot relative to E, the width of the line. So what happened is there is two lines here. They represent the width of the lines, the width of the line E. And this is the -1 line,